Say welcome to the Deep Space Exploration Society and our evening science uh, presentation. And tonight we are going to review some of the deep the what we refer to as our own DSN network, along with some other information too. One of the things that we have not publicized just yet, which we're going to, is the fact that the Deep Space Exploration Society is now officially selected by NASA to work on the Artemis II project as one of 35 other uh, entities around the world to monitor their signal frequency, which is going to help NASA determine the speed of the Orion capsule. And I'm going to be sending out a press release. I got some feedback from NASA, and I changed a few things, but I haven't as yet got it in the format that I want to send it out. But I'll try to send it out tonight to everybody, and also send it to a couple of media outlets that we have. So, in the meantime, um, I would like to
Hey,
ask,
Paul, I just wanted to jump in. You are sending it to Betsy, right?
yes, she's on my list. Thank you, Megan.
Perfect. Yep.
Actually, I'm going to have a special version just for her, but I'll send her
I
both.
love that. Yeah, that works.
Right.
The well, I should have reached out earlier. Their cutoff is Monday nights, so it won't hit next week's, but it'll hit the week after. Either way.
Yeah, I can send it out tonight before I leave. Before I leave, before I go off. I'm not going to leave. I'm going to stay right here. But in the meantime, I wanted to see if there's any other questions, by the way, while we're chatting for a second. Okay. With that, I'm going to ask Alex if he has something that he'd like to share.
Yeah, okay, I need to get it done. So give me a
I
second.
like your shirt.
Am I only one?
You got two of those, right? But yeah, you only
All
want one.
right.
Like, I'm
Slideshow
trying to stay warm.
and share. Like you, I have too many screens. One, two, three, four screens. Make sure I gonna. Okay, share. Do we see it?
Looking wonderful.
Yes, we see.
All right. Well, I'll try my best. Actually, it's more than I expected. Last minute revisions. All right. DSN, which stands for Deep Space Network, Beacon Field Test results. Well, as many of you know already, since I posted on Groups.io that we conducted a first ever field test, antenna beacon field test, which was, I'd say, pretty successful for the first run. I wasn't certain about a lot of things, but I also learned a lot of things. So it was very good, even though the weather was not cooperating first day, but second day was beautiful. So, well, second of all, thanks to everyone who participated and volunteered. So I gotta remind a couple of things. I mentioned that in my previous presentation when I described the DSN beacon itself. I'm gonna touch a couple key factors here. So why we need the beacon in the first place and why it's so important. Well, everyone know that it's a control stable non-reference source, right? Like use a signal generator when you do some bench tests and things like that. So, but it's critical also when you do a field test, it's antenna pointing. So this is like all time when the computers were not exist and people were designing antenna, what they were doing is to understand what the pattern is basically going out to field, place antenna, and measure the signal in certain points along the 360 degrees pattern, and just manual plot that. That's how it was done before. This is the best practice. Nowadays you have a simulation software and all that can do that, but that doesn't mean that the reality matches the free space calculation simulation. So it was important to understand what's our antenna pointing and is there any errors, and do we need to have any alignments. So also it also helps to understand if RF system that it's used to verify the performance, such like sensitivity, gain, and all of that. And in our cases, also was easy to verify the software that we wrote for DSN detection, if it's performing well and is actually detecting the signal. While other propagation experiments and the link verification is common sense, and it's easy to understand, do I have a path, and if you want to understand what kind of propagation and the different frequencies, so the beacon test is always the first thing to do. For our case on DSES, it's important to understand antenna performance for following project like Artemis, Moon Echo, so we did do some scientific research on that, and Venus as well, and Apophis, and many others that we're going to be engaged. So quick, this was the final beacon design that was finalized and implemented and performed well. Anyone would have a ability to look at that, and so I'm not going to describe all these RF parts in there, but everything was purchased online and very cheap and very easy to build, except the bandpass filter, which kind of custom. You're not going to be able to find something like that, so I had to manufacture my own. And as you can see, this aluminum, the copper pipe right there, the copper tube, is actual filter. It has 1, 2, 3, 4, so it's a three poles. And the reason we need to have a bandpass filter to extract the harmonic, correct harmonic, so it's filtered, which was successfully done, and we can prove that it's also working well. This is not just the one frequency, it's a programmable PLL, so you can actually program many frequencies, and I have a presets there for the 3 frequencies that mainly we're going to be using it. It will continue field testing, so we're done on 8420, which is DSN, and the actual frequency of the Voyager one. But we also can verify later on as a second phase of the beacon test the S-band antenna performance, and we already know how antenna perform on 23 centimeters of EME frequency, but it's also good to know what is a pattern and so on. So this is how the beacon looked, and also included initial budget link calculations. Nothing interesting, I just understand what the numbers are, and to make sure what we expect, and even that's 0.4 milliwatts is detectable in what the expectation of the signal strength, which is obviously in that such a short distance, which I use for calculation 2 miles, was obviously signal was very significant, even though we still have free space loss about 120 dB. But don't forget about the enormous gain of the antenna itself. So continue. So beacon location, we had the debate where we're going to go. I'm not familiar with the site, so if you look in any direction, it's kind of plains and kind of see the horizon. So for me, it wouldn't matter which direction, but Roger suggested that the south direction, it's a perfect, and I agreed because we don't have any obstructions. So different directions, it's kind of, we have like a scaffold. If you do 270 north, if you do 0 degrees, that would be the building itself. If you go to the east side, so it's going to be the trailer and the other antenna. So south kind of clear, but I wasn't sure about the elevation and line of sight. So Roger ran there and did some surveillance with Doug, and they find out good site, good location. So, and we decided to use that location as our initial beacon test. So I just plotted on the Google map, as you can see, that straight line. And we initially measured the coordinates of the antenna at the base. to match those coordinates at the beacon site position. So we would have as close as possible to 180 degrees south direction. So we'll also measure the elevation, and elevation at DSES antenna was 1318 meters, and elevation of the beacon site was 1329. So those numbers are important for estimation calculation on the further slides. So, but as you can see, it's not much difference. And I had to use meters because everything that we do in science, we mainly primarily using metric system. So if anyone had trouble with meters versus miles, please let me know. So beacon location settings, a beautiful photo that Roger took, and I think he used a binocular or something. That's why kind of odd round shape. But you clearly see the beacon on a tripod, and you see at on the horizon, it's kind of hard to see, but that's a small dot there, and that's the DSES dish. So we had a pretty good line of sight, but the visual line of sight is not the same as a radio link. So we're going to go through all that later on. So the distance was measured between two coordinates. Turns out it's 13.48 kilometers, which is it's before the Earth curves, so it's good. Were previously estimated about 9 to 10 miles. That's what they basically start losing the horizon. But 13 kilometers is definitely before that, so it wouldn't problem. So elevation point was when I did some calculation between the elevation differences. It turns out the elevation angle is only 0.003 error, so which is insignificant, and there's no way to use this error by adjusting the antenna. 0.003 is kind of small, so we decided to use as close as possible to that angle level at the antenna. But it's kind of hard when you do manual. But we're able to get closer as 0.05, which is 0.02, which is not too bad. It's still within the estimated beam width of the antenna for the frequency of 842 gigahertz. So for the antenna, we used just the open waveguide adapter, WR90. It turns out the most efficient and has roughly about 7 dBi gain. So it was used as a radiation antenna. So what were the initial objectives of the beacon test that we predetermined? So what we're going to do with it? Okay, so we're going to go there. We're going to set up the beacon. So what next? So we got to have a plan. So I kind of bulletized the simple steps that I had in my head that would be important to calculate the rest. So the first, obviously, we're gonna point the antenna at as close as possible on the elevation angle, which was 0.005. That's the closest I can go. I didn't want to run over a 0 point. And find the maximum signal by moving antenna left and right plus minus 5 degrees from the initial signal point that we determined as the peak signal. And also slow antenna on elevation, obviously plus side to plus 5 degrees, but obviously was way too much. But it was just initial determination that let's have some numbers. Realistically, until the signal lost. And keep in mind, we didn't have initially when we start testing the attenuator, so we were expecting the hot signal with the maximum 0.4 milliwatts. But Roger had 40 dB attenuators with him to attenuate the signal as minimum as possible. So then when we slow antenna back and forth, we determine where the data is consistent. So where we actually determine the peak, there is no side lobes and there's no any diffraction, reflections, or something like that going on. So it kind of took about 5 to 10 different tries to identify the signal. While we was doing this, we were steering antenna manually. We could not do this in auto mode because there's no way to stop an exact position. So it's only manual operation. So, and then if we determine the signal is there in a certain azimuth, and we have to reduce the signal until we have sufficient signal noise ratio for calculation. And that's why we added 20 dB attenuator. Then another 20 dB determined a 40 dB attenuation with some losses between additional 2 dBs. It were sufficient to have a signal noise ratio in that distance. And at that point, we started doing finalizing the measurements to identify basically the pattern, the beam width of the antenna. So, and also I was watching the drift, making sure that there is no false readings. We don't have anything all of a sudden the signal peak is going up and down. There are a lot of when it comes to microwave, there are a lot of other aspects affecting it, and I want to make sure those factors are not affecting and not misleading the calculation. So it took about close to about 45 to 1 hour, 45 minutes to 1 hour to get all this concluded. And all that time, Roger was hanging out outside in the field. So kudos to him for that. Well, what kind of hardware we used here and what was involved in the DSN? We used the actual DSN RF system that's been designed and built for DSN probe detection that was actually installed. So it's another a point why we need that test. So we have to kind of verify multiple parts, just not just the antenna pointing, signal detection, the software performance, the equipment performance, but overall how everything working together. So, and I used the first time my new design system, DCPM, which is the data collection and processing module, which we're going to replace the first generation on Raspberry Pi 4. It's more sophisticated with 2 computers on it. Well, I described already that. I'm not going to go through it. I added the power supply for convenience and a feed motor assembly to control the feed, adjusting plus and minus on the x-axis to determine the focal point. That wasn't done as expected. A few points were missed, but I was able to determine the maximum signal at the point or the system allowed me to move it. And the software used 2 types of software, so make sure I have a redundancy in the detecting signal of both. So one was the DSN detection software. I wrote on Python code for the actual DSN detection. And the second other one is just GQRX SDR software. If you're familiar with anyone in a Linux environment, it's similar to SDR Sharp software. So that important to have calibrated readings. This is how the DSN RF system was installed on the feed and looked like. As you can see in the bottom, I kind of put annotations so make sure you know what it is. So the top portion is the DSM RF system itself, which includes the feed, the polarization switch relay, Cox relay. On top, the black kind of strip line is the filter, very narrow, insertion loss about 0.3 dB, which is very good. It's about 8-pole DSN filter, and then the down converter itself that has a preamplifier built in on it. So we didn't need it external preamplifier for that matter. And on the back, there's an SDR receiver and the clock reference installed. So everything in such a small box, about 10 by 4 inches size, and has just USB connection and power connection to it. And everything sits on top of the platform, the feed motor assembly. They're using the actuator and a linear actuator, so it goes up and down by about 20 centimeters by 10 inch. Have a length of adjustment. That's for the focal point. But inside the feed, we have all the equipment installed on the awesome platform that Roger built, the same platform we use for each project. Very convenient, very easy. So everything mounted to it, and you can remove completely without deattaching the each module. So I have a redundancy the 2 modules, and another thing why I had these 2 modules, I actually planned using 1, but because we had only 1 fiber optic line, and unfortunately the passive fiber optic splitter didn't perform well. We decided to use just the 1 system. So the top module, basically, it's a first generation of the DCPM, but has already a stepper motor controller inside, as well as the SDR processing data and the software inside. So and the power supply on the back. I'm sorry, on the bottom. And there's a high-speed USB for different reasons. So I could locally connect the computer and the keyboard and the monitor to program or change something. If it's remote side, it works. So a lot of things that for debugging and programming on site without removing anything. All right, so the fun part here, calculations. So I'll try to be not too much into it, so everyone will have access and could do it. Obviously, I didn't want to do everything in the manually because it's a lot of work. So I used the obviously help with the AI to calculate, but make sure that all the initials and everything is correct. So we had the beacon site, our beacon RF site, and where we already know that we had about power about -4 dBm. So we had the attenuator on about 42 dB total attenuation before antenna, and antenna plus 7 dBi. So absolutely all this calculation is simple. Your P formula, the estimated isotropic radiated power, turns out your power is about -39 dBm, which is pretty small. It's about 126 nanowatts at the site. But this is expected, and this is where we really need it to make a signal super weak, so the antenna will detect as minimum as possible. So that was the initial decision. So if you calculate the free space loss between the antenna site and the beacon site, it turns out that 13 kilometers is roughly about 133.5 dB free space loss. Now, if you take that loss and remember in the formula, it's going to calculate the DSES based on the DSES site RF data. What would be now our estimated signal at the antenna? So we know the antenna diameter is 18.2 meters, and the wavelength for 8.4 gigahertz is turned out by 3.5 centimeters. So assuming efficiency, dish efficiency is 0.6. I mean, we always use 0.6 because it's kind of nominal. It's kind of conservative number. I have not seen dishes with the efficiency below 0.6, like actually before 0.5. It's impractical. I mean, you can't use those dishes. So you make sure that your efficiency, it's a 60% at least, and go higher. What comes to it, that means it includes all parabolic shape and all of that. So normally 6 is kind of conservative on the minimum side. But normally, if you take radio astronomy dishes and like TV dishes, the good ones, their efficiency is more than 60%. So the coefficient 0.6 is basically 60%. So antenna gain turns out with those numbers about 60 dBi. Well, it's very, very high gain, right? And we never used this antenna on those frequencies. So for us, it was unknown territory, and that's why it was important to understand the performance. Is there a really 60 dBi gain? Is it really the beam going to be that narrow? So it's a lot of questions that we try to answer, but unfortunately we can't answer all of them at once. So the estimated beacon signal, if you take all this calculations, it turned out about minus 112.5 dBm at the feed side, which is very good signal. I mean, it's hot signal. It's not something very weak. And if you take a noise floor, at 140 dBm, that easily can be achieved. I mean, this is kind of very good signal noise ratio, it turns out. So, and then you take all these numbers and plug in and start to calculate what's my the front end calculation. So we're actually, my signal noise ratio going to be observed. Then you need to understand what's your losses, what's your noise figure, what's your resolution bandwidth, and all of that. And when you plug in all of that, so we know that the noise figure is about 1 dB. Once again, some of the numbers are estimated based on manufacturers provided. I had no ability to actually measure noise figure. Perhaps noise figure can be 2 dB or 1.8 dB. All those tolerances could be applicable to the final data. So there are something that needs to consider. The numbers cannot be correct because a lot of numbers that we use is just provided, so not actually measured. Well, there's a certain what you can measure and then plug in a formula based on known factors and known constant, what you're going to get. So that was the important. So the antenna polarization loss is 3 dB because at the side, the beacon side, we use a linear polarized antenna, the waveguide, so it was vertical polarized. And we used a circle polarized antenna. So if you take circle polar antenna mismatch with linear polarized, it's about 3 dB. That's what's normally, but once again, it could be a little bit slightly more, but what we consider in equations every time is 3 dB. That's what it's defined mismatch loss, polarization loss. So the estimated signal noise ratio would have been 40 dB. So this is the power based. The power based means everything that comes in dB and the measurement antenna is all power based. Now, if you take SDR, the SDR it's FFT, so it's a different as a magnitude. So we have to convert all of this to make sure whatever we're going to measure would be correct. So I didn't want to include all of this calculation here. Kind of, it's not a science, but I have everything. Is anyone interested or want to do on homework? Go for it. It's all easy, and I just trying to minimize and just get to the point where we at. So when we use the SDR software KQRX, so we determined that absolute. I guess I lost the audio.
Yeah, you're still on.
Oh, do you hear me?
Yes.
Okay, sorry. That my headphone said that is disconnected. I'm using the Bluetooth. So okay. So the absolute noise floor was measured at minus 115 dB samples. So it's absolute noise at 38 hertz resolution bandwidth with given FFT number. So I don't want to go in detail that everyone who's familiar with FFT and SDR so know what I'm talking about. So so minus 99, it's not real numbers to compare. It's just basically the decibel relative to the full scale. That's what is considered. So you're really looking at the delta. That's all you care. And they convert that delta to your number. So as you can see, like someone probably noticed, like, oh, we have 40 dB there and why 16 dB there. So what's up going on there? So one is a power based, one is just magnitude based. So anyway, moving forward. Well, anyone has questions or concerns, please stop me and we're going to cover that. But I want to make sure that I value your time, so I don't want to spend a lot of time on talking about this. But so now, if you convert the RF signal noise ratio versus Fourier's transform signal noise ratio, and turns out that it's right here. Oops, sorry. So 15.3 dB. This is after all this calculations, you have to consider bandwidth per one beam. Then you have to correct the window. Then you have to also calculate the mismatch processing gain. Now, all those based on the settings, you have an FFT SDR receiver and FFT processing on the window. So I just captured the plugin number there to understand how close I am. So it turns out that it's about 15.3. So the formula on the bottom does actually all these numbers. You just plug in there and that's what you need to get at the final signal noise ratio of 15. So if you compare that, so we measured the real signal noise ratio with the polarization loss about 40 dB, and obviously I didn't see the 40 dB there, and I'm never going to see this. So if after a calculation, it turns out that expected the FFT SNR, so a magnitude based, would be interpreted as between 12 to 15. So we observed about 15.8 or something, 15.6 or something. So it turns out between that. So we're kind of close, but I was like, wow, that's when I did calculation, it was impossible to be so close there, right? So I ran numerous times to be sure I didn't miss. So first of all, I missed the polarization mismatch. So kind of didn't think. So I added additional 3 dB. But once again, there's a lot of things that, like noise figure, like losses, the true losses, like I don't know if the antenna gain is actually 60 or we may be out of. So there's a lot of factors that might affect the number, plus and minus. But I tuned myself to like it's going to be plus minus 3 dB. So it turns out it was kind of exactly what I expected. Now, Skip asked me about personal calculation. I'm like, I did not include that, then that's my bad, because when I normally calculate the microwave links, the Fresnel is obviously is very important, and I want to make sure that someone don't understand what is a Fresnel, what is a Fresnel zone calculation is. It's and why it's important. So what comes to microwave links, the ground in effects, and there is the zones. The first zone is very important. So it's used for any microwave link calculations to determine actually how much the power of the signal comes to the site intact, and even though if you're in a clear site. So I give you a little example. In September, August, September, it's RL 10 gigahertz and up contest, and that's the best contest for me. I love to participate, and normally I do rovering, and normally I go to the sites. So this time we went to the mountain south of Tucson. It's about 10,000 feet elevation, pretty good one. And we tried to cover the long distance. And we were successful. Two of us were there, and we were able to communicate on 10 gigahertz with the another amateur radio guy that was on the top of the mountain in California. So, and it was unbelievable that I broke my own record. So it was about 870 kilometers on 10 gigahertz directly. So obviously there's absolutely no line of sight, right? It is too far, even though the both elevations were about 10,000 feet, about 3 kilometers above the ground, is still not enough. So I thought in my mind that's going to be the airplane scatter, but there was an airplane. It was actually a troposcatter. That was my first contact using the troposcattering on the micro frequencies. But why I keep mentioning that, because when I did all these calculations, I had to write the special script to do that. The Fresnel was the zone was very important because it affects your propagation link, so it has to be accounted. Besides, there was also the atmospheric loss that we did not include here, which is insignificant. Probably, I would say probably zero point 0.1 dB would be at max the propagation atmospheric loss on a gigahertz. So I didn't include a lot of factors because I thought they're not significant. So this is the topography of between the DSES dish and the beacon. So I just use the Google Earth. I mean, everyone has Google Earth, I believe. I use it a lot, especially for the planning to microwave contacts. And the lowest point here on the left is actually the DSES dish. This is our DSES site. The right corner on top is the site when the beacon was when Roger went. As you can see, this is topography, and it's kind of line of sight, right? But the Earth is not just simple like a flat line, right? There's some different um, hills and everything. So all of this is important when you do calculations. So anyway,
Alex,
yeah,
that looks
yes.
like a lot more than the what was it, 13 meters of separation.
No, it's
What is
8.8.
the scale on that on the left
It's
side?
it's 8.4 miles on the bottom, so it's 13 kilometers.
I mean the elevation scale on the right-hand side.
Oh, the elevation scale, it's 4,300 versus 4,354.
It's like about 50 feet
Uh,
between.
4,294, and I don't see that, but it's it's a 1318 and 13,929 meters. So it's 11 meters difference, something like that.
Okay. Well, that's pretty good. Okay.
Yeah, yeah. I mean, I didn't have set up in metric system on my Google Earth, so
Well,
didn't need it.
the other question I had was
Yeah.
how much the beacon itself doesn't have a horn or anything. Was there an antenna gain? Maybe I missed that, but is there an antenna gain of the beacon?
Yeah, 70 BI.
So, okay.
Yeah, that's
Okay.
over isotropic, so it's a
All
free
right.
space gain.
Okay.
Once again, is that really 7 dBi and the particular one? Well, I don't know. I haven't tested. I just go with the normal, what we normally use for the waveguide adapters. So, and that was predefined. So once again, there's a lot of tolerances that affect the final data, but you have to be close as what you expect, and that's the bottom line. So continue the calculations. So we normally the best of engineering, we always use 60%. And that's what I use as a default in all my equations for the first personal zone. So, and why is it 60? Because below diffraction is you have losses and rises rapidly, and you have to be 60, you know, and then that's what you ideally want to be, and to when you plan the microwave links. And then when you have different elevation, that might affect it. So you have additional losses just because of that. And that was a very good point that Skip brought up. I'm like, I did not include, or I did include, but I just simply ignored it and didn't post it that. So I tried to re-verify all these equations again, and that's why it took kind of time to verify the links again. So we calculate, I estimated that's about 11 dB loss, turns out, in just Fresnel itself. And then I start verifying, do I have this implemented in my equation? I didn't post all the equation, obviously, for a very simple reason. I don't need to. That's not something everyone going to look and be excited about. But once again, everyone can do it. Nowadays, you can just plug in and it'll calculate for you everything. So for me, it's important that the final data match what's supposed to be. So I have to verify every single equation. So after verifying, it turns out here, if I would not include the fractional loss and that would be incorrect, then the difference is obviously 11 dB between these two numbers. And if I would have that, well, I would never copy signals, right? It makes sense because my signal noise ratio was about 16 dB, something like that. So if you just add to it plain 11 dB, the signal go into noise. So that means the reality and the calculation kind of match, but what certain accuracy, I don't know. I cannot determine the accuracy. I go what I can calculate and estimate it based on my ability with the known known factors and numbers. So turns out we're darn close where we're supposed to be. So we estimate about 40.1 and about computed SNR with the loss accounted is about 40. So, well, I recalculated the number again a few times. It turns out the same all the time. And that includes resolution bandwidth, includes thermal compensation, as many factors as possible. Once again, are they correct? I don't know. I use the default numbers for something that's supposed to be within that. Now, all of that, the second part is, okay, with all these known factors, what we have and the numbers what we measured, can we estimate the antenna beam width? And what is important is, okay, I detect the signal. Now when I start moving antenna up and down, left and right and up and down, and for me important at which elevation or azimuth the signal disappears and how it disappears. Is it gradually disappears or simply just drops and then reoccurs again? So that's why I was running back and forth many times. Doc was next to me sitting and I was observing all of that. So we're about, moving back and forth about multiple times, about 10 to 12 times in just multiple direction to determine all of that. And when I determine the numbers, I just plug in numbers to calculate and draw that pattern. So it turns out that the calculated half power beam width, which is at minus 3 dB, obviously, at that particular frequency, if everything as supposed to, it would be 1.137 degrees, which is kind of narrow, right? And it's like, it wondered, like, such a narrow beam width, will I able to even move antenna at such an accuracy? So when I started measuring the actual beam width using the beacon signal, so we picked out an 179.8 degrees, kind of 0.2 degrees off the south, due south. So now I don't know, is that because the antenna pointing area itself that we never noticed? The 0.2 is kind of small. I mean, we would never notice that if we have it in real life, because pointing to pulsars or anything we've previously done, 0.2 degrees, it's might not going to be even visible there. or because the GPS readings and the beacon location were wrong and digits were off. But I think Roger did good job to match all 6 to 8 digits. So I think that's pretty damn close to, but still, 0.2 degrees is kind of something that is still debatable. I mean, I'm going to go through like, oh my God, it's 2.2, but it is important to know. And
Alex?
yes.
Yeah, I want to take another shot because at that because yeah, I could have an error on my end, the positioning of that. So I would think that your second bullet would be more likely.
Yes, that's good, and that's what exactly going to do. But that's initial test, and it was important at that moment. But even there was an error, right? And once again, it's hard to determine what is the error, but we can prove that by doing not only the same test, but also verifying on different frequencies as well. So based on those estimation, I plotted, and it turns out at zero point 0.3 degrees, if you move antenna at 0.3 degrees plus and minus an azimuth, the signal disappears completely and blended with the noise. And then when you start approaching close to your peak azimuth, which is 179.8 degrees, the signal reappears, and it reappears very gently slow. And I use numerous times to understand how slope is on both sides to understand there's a side lobes. But with this signal loss ratio of about 16 dB, it's hard to determine, but it would have been visible. But I like the way how slopes on each side were pretty identical. So anyway, this is what we measured derived of the angles. And then we started comparing now what's our differences between what we actually measured and what we calculated based on antenna performance. And the difference turns out is 0.003 degrees, which is absolutely insignificant and negligible because we can't just consider 0.003 degrees it's ever going to be our accuracy. I was like, okay, well, I'm kind of satisfied because first of all, that not just one signal to ratio kind of matching, but antenna kind of makes sense. Where we can be off and not be precisely, slightly bigger, but once again, there's factors applicable and my affecting it this. But are we far off? No, we're not. We're within the envelope where we're supposed to be. So it's exciting. So, and then when you know this, you can actually estimate, calculate what would be your first side lob. And it turns out it's about estimated and calculated minus 20. Well, and it is absolutely no way I can measure minus 20 at that particular time with the 40 dB attenuators. So the next test we're going to be doing, we already know expected the first side lobe going to be minus 20. So we just need to make sufficient dynamic range of measurement so we can detect the 20 dB difference between the peak direction and the first side lobe to see if it's actually close to the number that's being calculated. Now, efficiency calculation. It's one of the also factors that important to understand. Since I previously mentioned, kind of determined a 60%, which we normally use as a standard. I use 60% for all equations for the moon, for Venus, and everything. But if our antenna efficiency higher than that, so it only helps, right? It adds more gain. So if we consider, all the numbers we determine, and a simple calculation, which is, as you can see right there, and it turns out that the efficiency is about 82%, close what you at between your ideal and measure it. So, but obviously, I don't believe that is the truth, but it's still it tells me that based on observations, calculations, and I'm pretty certain that the FD ratio of our antenna kind of matches the feed FD ratio. That means we're pretty not over eliminating and under eliminating, so kind of darn close to the gain what is expected to be, so close to 60 dB with the 60% of the dish elimination efficiency. There's also another factor as a surface efficiency that's kind of like a third there, but I'm not sure how we can determine that and measure because it's kind of important on the microwave frequencies. That's why all these TV dishes they're solid metal, right? They're not mesh and all of that. And I did some research, and normally the surface efficiency for the radio astronomy dishes I don't think our dish falls into radio astronomy as intended to be built and used for, but it's roughly between 70 and 80%. So even with the 60%, I think we're still good. But this is important to understand because it will determine the actual characteristic of your dish when you want to use this dish for something that's far away and very weak, like Voyager or anything else. So this is actually important to understand what was the actual RMS surface error is. But that's yet to be determined. See what we can do to understand that.
Alex, couple of
Yes.
things. When you do this, it looks like are you assuming 100% illumination of the dish with the feed?
Well, we're
Like
assuming
you're utilizing 100% of the dish to
no, I'm
get.
not. When you do calculation, you can't assume anything. You just go with the numbers you have.
Yeah,
It's
but what?
estimated.
Yeah, but what I was thinking was, yeah, you got a very narrow beam width from the test,
Right.
and you're assuming a 60% efficiency. And does that take into account um, how much illumination you have of the dish? Like if you're under illuminated or over illuminated, you're going to get a different answer, right?
Right. And that's why you're never gonna get the level what you expect to get. Make sense?
Right.
Because illumination will affect your gain,
Yeah.
directly affects your gain, right? So
Yeah.
if you have a lose of 5 or 10 dB gain at expected signal with the signal noise ratio of 15, guess what? You're never going to measure 15, right? So obviously, based on the numbers we obtain and the calculations, once again, it could be some tolerance applied, right? But definitely not 10, 15 dB, right? So
Yeah.
we that determines that the efficiency is pretty close. Is that 100%? Obviously not. There would be never 100%, right? Is that 90%? No, it's never going to be never. But I'd say between 60 and 80%, it's a very good chance that we fall somewhere in there. And efficiency is also dependent on the frequency. That's why when you have the RMS surface error account. So none of that ever been done. I'm pretty sure when whoever designed the dish right back then did some calculations, they had no way to verify that, but they should have. If you look at the original data sheet or of the dish, am I going to include all of that information across the different frequency range?
Hmm.
Any comment?
Well, yeah, the other comment was you've proven a very narrow beam width. And if we try to track any of these deep space probes with that narrow of beam width, we may be able to do it with the encoders, but it's going to be difficult to get onto the object and find it because of the narrow beam width. And so what I was wondering, is there a way to reduce the gain and take less illumination of the dish, like with a horn or a chaparral antenna, and broaden the beam width so that we can actually achieve a lock on the object?
Well, I have a slice for GSM, so we can get there to understand what we're looking at,
Okay.
and that's yet to be also verified. One test can conclude everything. I'm now looking here 100% determination of the antenna performance. We're only looking at DSN frequency, but we can look at the other frequencies as well and to understand the performance and then correlate all of that as possible. So I'm not going to conclude anything and determine that what it is, and also make suggestion that we're going to do narrow beam width versus high beam width. I'd like to keep the antenna performance as supposed to be on those frequencies. There are limitations for the frequencies we can use. I was surprised at the antenna performance
Yeah,
on
this
the
is
8 gigahertz.
impressive for eight and a
Yeah,
half gigahertz.
yeah.
Yeah.
Trust me, I was not looking positive to get any data whatsoever, but it checked out all our boxes. But there
Hmm.
is something I'm probably missing. But once again, the intention of this presentation, not to go through all science and physics, which I actually done many times, and just today as well, to verify it and be sure that numerous times it turns out the same. But there are some possibly missing points. But that's why you guys are here to discuss that perhaps in the next conversations. But I'd
Yeah,
like to
that's
finish.
that's why I bring it up, just to make sure that we're thinking about that, because uh, from this data, it would appear that there might be an issue with getting a
Yes, and
lock,
yes, and
right?
it will be. So let me
So I
continue.
can make that assumption without the full analysis, right?
Yes, yes. Well, it's good because I like when people talk. I like when people comment. Right? It's stupid when I talk and just everyone blindly looking at. I'm like and listening. I have no idea. So I'd like to have both way communication. Right? So I'd like to continue the presentation
Go
to
ahead.
just get the idea what we at and what we determine. And once again, that's yet to be verified. Um, I was planning to do more tests on that day, but we were running out of time. We all have to leave. That was done on Sunday. And we planned to do this on Friday, but unfortunately, the weather was horrible. The wind was enormous and cold and chill and snow. So weather was not cooperating. Then we had problems with the fiber optic. So we lost a lot of valuable time. And unfortunately, we had just a very tiny period of time to conduct this test. And I was very excited with all these test results. So I'm not going to complain about that, but we'll come back to this testing to prove a couple points and verify multiple things. So based on those numbers we obtain, uh, and then we can draw the calculation. And I do this at my work, and it's not a big deal. You don't need to be a truly antenna scientist to do that. It's very simple nowadays. You have a perfect tools available to do that. So, and I plotted the beam width and numerous pattern presentation in a polar and then Cartesian, because that's what I do in electromagnetics. In professional world, we use mainly Cartesian beam width plotting and doing this professional things I cannot disclose. But this was very simple, just plot it and see where we at. So if you look at the Cartesian plot pattern, so you see the blue line as a measure that we actually, from the beacon numbers derived from this 0.3, and as well the theoretical is. So I have seen this many times when I did actual tests on numerous different antennas and Gauss beam antennas and lenses and all different frequency ranges up to 134 gigahertz. I've seen similar pattern every time. You never ever follow the theoretical. You always slightly off, and this is the follow same. So it's an ideal world in an ideal free space. You get the best results, but in real life, this is what it is. So if you look on the radius on the polar projection, and it's kind of like what you see your 0.3 degrees here in the beam width, which is majority of your power density of the power is in the middle portion, and then you have a power dissipating over distance. But I'm not going to talk about the near field versus far field. That was not objective, and I don't want to calculate was my near field far field transition zone. Not important, absolutely here, but we're looking at obviously far field. And at the point that the beacon was is definitely far field. So that's very important. So and based on that, what we measured, obviously in 0.3 degrees and a radial pattern, you see that the signal is completely disappears. So now it's important to kind of visualize that, but numbers actually also plain. And I say, okay, well, let's compare it to the moon. So what if we're going to point this antenna to the moon? I don't know what for reason. Perhaps it's something DSN probes and anything that operate in X band, but I don't think so. I think they're operating on the S band, not X band, on sublunar orbit. But anyway, the point is just like projecting the moon on top of the antenna beam width. And if you compare to, let's say, 1.2 gigahertz, like the ME package we have, right? I mean, your beam is going to be over. So even you off the moon, you're still going to copy. And we've done many times the antenna stopped tracking and whatever reason got error and the signal's still there. I'm like looking, I don't see even moon on the screen, but you still copy the signals. So the obviously the beam width is a lot bigger, so the pointing accuracy is insignificant and negligible. You don't care about that. So here, as you can see, your moon actually, your beam width, it doesn't even cover the moon disk. So you have to steer antenna to scan it. So this is just a visual indication how narrow beam widths are important, depend on what you're trying to do. So if you look at the moon radius, is 0.25 degrees, the radius. So and a minus 3 dB our radius of our beamwidth is 0.0083. So it's a lot smaller than the moon itself, and that's about 3 times wider than half power beamwidth what we have. So, and if you translate this to pointing tolerances using the moon as an object, as you can see, like 0.05 is still near peak. That's what you're going to have a measure the maximum signal. If you're going to be within 0.05 degrees, you're going to be right spot on. And if you're going to move this to 0.08 now, plus another 0.03 degrees, you lose 3 dB already. So that's your actual cutoff of your beam width. And then moving higher and higher, if you have a tolerance of 0.25 to pointing error, you're going to be off the moon. So this is what we're looking at. And the conclusion that for the moon in particular, in this particular comparison, 0.1 pointing error costs your real S signal noise ratio. So you basically lose the signal. And that's really important if you're looking for the weak signals. If your signal noise ratio looking like tracking Orion rocket that have 60 dB, and if you have a pointing error on 0.1, it doesn't matter because you still have a plenty signal noise ratio. So it's important to understand that the weaker signal is, and as more affects the pointing error. So I try to plot this pointing error and using just 2 points and previous calculation, but we can do next testing and drop more points with the higher signal to make sure that those points are along this line. But I'm pretty sure it's going to be close as possible. In my professional experience, it's always been closer, but it might be something else, but I'd say it's going to be pretty close. So now based on that, we kind of can estimate what would be the pointing error. And obviously it based on the signal outside of our full beam width of 0.8 degrees. So it's kind of, as you can see the line, it's kind of visually you understand where you're supposed to be, what is your envelope. Now, all of that leads to the important part. Why is 8.4 even care? Why we do care? Well, we care because we're trying to detect Voyager. And we don't want to spend weekends and months trying to detect it without any success on why we're not even seeing it, what's going on. Alex, your system is piece of crap, doesn't work, or something else. So we want to make sure that all puzzles, pieces of a puzzle are visible, so we understand the whole picture, who to blame. So, and if you apply this pointing error versus the DSN probe detection, and let's use the weakest one, which is the Voyager, the signal is it's a very low. It's even hardly detectable on a 20-meter dish. You have to use the system integration. There's no way you can point and, oh, there we go, there's a Voyager on my waterfall. It's never going to happen. You have to have a system integration. So you have to accumulate the signal over time. But there would be no signal accumulation if you're off 0.1 degree. So you're going to spend hours trying to detect something that you're off by that. So now we have some baseline we know. Well, once again, yet to be verified if it's solid or not. So let's use all these active GSM probes, starting with the Voyager and Juno as the second one, the weakest one, followed by New Horizons. I'm sorry, New Horizons, I believe the second weakest, not the Juno. It's wrong order here. Then Lucy, and then everything else is pretty close with a very strong signal noise ratio. So I wanted to actually detect those on Sunday, but none of them were available. All of them were below horizon, except Mars reconnaissance orbiter that was right at the sun. So Mars right now, it's near proximity of the sun, so everything that orbiting the Mars is actually within proximity. But with 0.1 degree beam width, you don't really care, but you still have a mirror dish, so it doesn't really matter. It's matter for your feet, but it doesn't matter for a hub and others. So it's a lot of infrared that unnecessarily. So that's why I decided not to do that. Instead, I was pointing to the moon, but there were no available probes at the moon as well. Anyway, so we know that our half power beam width is 0.167. That was measured, and we can calculate using this normalized pointing loss formula, and then attached to this. Okay, well, we have a bore-side signal noise ratio. So if you point antenna at the spacecraft, you're going to have, the maximum signal. Off the bore side, the signal is completely gone. So what if this true case? So what we're looking at from the Voyager 1. So Voyager 1, it's a signal by itself is very low. So any other additional pointing errors applied will completely compromise detection. So New Horizon, it's still low because it's far away as well. I think it's 800 something million kilometers, something like that. But your pointing error affecting it. Now New Horizon is, I'm sorry, the Lucy, it's closer. I think it's beyond Jupiter right now, somewhere in flying towards the edge of the solar system. It's moderate, so we can detect. So all of these space probes will actually give our more idea, Bill, because we're going to use them as a source to understand what's our pointing error, what is our signal noise. I'm sorry, the what I was going to say was beam width, and all of that. Because beacon is just a step, right? We know the antenna performing. We know that fact. Let's move on, right? Next to start detecting. Let's start with the strongest one. Let's take Asteria A, which is orbiting the sun. So that's the closest one. And I was going to detect, but it was not available at the time. I'm sorry, or was close to sun or something like that. It was a highly elliptical orbit. So anyway, none of those were available. So we'll start with those and comparing data from them. We're going to steer antenna left and right, try to understand the maximum signal and compare to data we already have and see, is there a delta between data here and data there. So that's my next step. Now, if you apply the calculation between the previous slide here, which you obtain your signal noise ratio delta, on top of the signal noise ratio error of your antenna pointing and the bore side SNR expected for the deep space probe, it turns out that we can plot we can put in the table. So if you take a 0.002 degrees offset, so the Voyager won't be detectable. Well, Voyager 1 cannot tolerate 0.05, which is very slow. I don't think we're able right now is our accuracy on our dish to do that, and that's when you do auto tracking. So I don't think there's any possibility to do manual tracking with that accuracy, because it's going to be constant antenna moving in both azimuth and elevation. So before we even attempt to detect Voyager, we have to make sure and practice on the closest one to determine what is the antenna pointing error. That is important and crucial. And right here, I compare that the Voyager 1 assumption. If signal noise ratio 6 dB, it's the one that I simulated with about 60, I'm sorry, it was 15 minutes of the integration time. I don't remember off the top of my head, of certain integration time, a 6 dB built up of the signal if you constantly pointing and tracking. So if you move antenna by 1 degree, or we have a error 0.1 degree, the signal is below detection. The integration wouldn't work anymore because there's nothing to integrate other than noise. Now, if you compare it to Juno, you see the signal bore side is 25 dB. That's what estimated we're going to detect pretty hot. With our antenna gain, we expect to see 25 dB signal noise ratio on detecting the Juno. Now, if you're going to move out of the 0.3 degrees, if assuming you have 0.3 degrees accuracy, which is we determine that's the beam width, the signal would be completely gone because the first side lobe is -20 and then you're gone. So anyway, this kind of gives you the idea what you're looking at, and any other DSM probes are stronger. So except the New Horizons, but it gives an idea what we're looking at. Now the conclusion, I don't have really conclusion. I mean, I concluded the test was kind of success. At least we understand the performance. It kind of matches what we expect. There's no significant differences in the numbers that I should concern. But there are some things that possibly missing in the numbers and slightly exact correct. I'm not going to go, it is exactly what it is. It's 40 dB signal-to-noise ratio, perhaps could be 30, 30, 38, could be 50. There are some tolerances involved, but overall, if you take all the numbers, they're all pretty damn close to each other. So the antenna, the bottom line, the antenna accuracy is very important, and that's a real example. If you're looking at DSN frequency 8.4 gigahertz, your pointing error, it's very important because it determines will I able to track it and detect the signal. As weaker signal is, they're trying to detect, the accuracy going to be critical. That's with a known beam width, which we estimated as 0.167 degrees as right now for DSN frequency. If we're looking for Voyager 1, well, according to the numbers, the 0.05 degrees, that's absolute tolerance of the antenna pointing error. So we cannot change that. Well, future activities, well, I'll definitely going to come back. We have an idea what we're going to do. I'll continue. We're going to replicate the same test, first of all, to understand are we consistent on the data measurements, and also I noticed the drift, frequency drift, because I did not have external lock on the beacon. So I made sure the drift mitigated. Even the drift was very small and insignificant, it did not affect, but it's also important to account. As well, I wanted to determine the solid pointing error. So we know for sure that there's antenna error across the multiple frequencies. So we can compensate that in the software. So that easily can be implemented. But not knowing that, we don't want to introduce any correction to something is not known and proven. So that's my point. All right, finally, questions.
Alex, yeah, that's a very good analysis. I'm just curious if you had an opportunity to optimize the focal point using your new adjustable feed.
Yeah, thanks for that question, Dan. I was going to do that, but unfortunately, there were mechanical issues with that. So when we Roger, can you explain that? So I don't want to explain this for you.
Oh, yeah. So unfortunately, we started getting parts up there, and as things happen, I started compromising the mount to try to get things to work. And it ended up that, Alex was able to move the feed toward the dish, but he really wasn't able to move it back from the dish. So that experiment still remains. And that
Okay.
should be far easier with the mount that I'm building.
Yes. So I didn't mention that, Dan, just for a reason because it's not determined. But since I was able to move the whole assembly forward, and I did numerous times, and I was checking the signal wasn't going up. The signal was going down.
Mm-hmm.
So, and determined like, well, it kind of needs to go back, but I can't do that. So that also part, and thanks for bringing up because I didn't include this in the error, that we might gonna have move antenna if it's focal point off, which is kind of would be very easy to detect on this wavelengths compared to other frequencies. So the signal gonna go higher by 2 or 3 dBs. It's already significant. But we need to determine that. We need to know precisely what the focal point is with the accounting of the face point, which is slightly inside the feed mouth of the septum feed, and precisely measure that distance from the edge of the hub to that point. And that would be equal for any feeds you're going to use, including the science feed for the hydrogen line and the pulsar detection and anything we're going to do. But once again, if we off this, you're still going to be able to detect, but you're going to lose your gain, right? And that could be sufficient. If you're losing 3 dB, it's still okay because the 3 dB signal below and your signal ratio is 10 dB, you're still okay with the 6 dB. So anyway, hope you answer your question.
Yeah,
So,
thanks.
Alex, this is Adrian. Just a quick question. So, all the antenna beacon measurements were done at the zero point 0.4 milliwatt beacon power output?
Yes.
Okay, thanks.
Well, with the 0.4 beacon output, correct, but with the attenuators, so we started without, we have plain 0.4 milliwatts. Then we start adding, because signal was hot, right? Even 0.4 milliwatts sounds like nothing, but the antenna 60 dB gain 14 kilometers away, it's still hot signal. So, and that's why we had attenuation. So how I know precisely it's 0.4 milliwatts? Because I built this beacon and I tested on my bench for days and weeks, running the power stable and tracking on the Rode-Schwarz signal spectrum analyzer to make sure the signal amplitude is not drifting as a constant and everything. So, and that's why I determined it was actually 3.86 dBm, something like that, minus 3.86 dBm, kind of stable. So that's why it was translated to 0.4 milliwatts. We attached the attenuators, which is 20 plus 20, with the two adapters and a waveguide. I measured the losses as additional 2 dB losses for 8 gigahertz. So the total attenuation between the 0.4 milliwatts to the antenna was 42. And that's what number I used with the plus 7 dB estimated gain.
I see. Thank you.
Any other questions?
Yeah, Alex, this is Dave. I know that you measured the power output on your Rhodium Schwartz. Couldn't you have used the signal level then through your SDR if you locked the AGC, for instance, to get an independent check of the losses?
Yeah, David, good question. I was running out of time, and I wish I could do a lot more experiments because here's the deal. When I was able to see the signal, I was super excited, and I tried, and I instantly added numerous other steps. And I look at the time, we're running out of time, and I didn't want to hold people there, and that's why right now I have a lot more things to do and compare different software. Actually, I wrote another software. Not a wrote, I already have a software. I just implemented another block there. They're going to give me actual calculation that me going into Google and Chat GPT and doing that, I can actually comply all data within the code. It'll give you instant results. And what's important is resolution bandwidth, the especially kind of gray area is FFT. And I was based on those settings that I had. But I believe I had set a 10 dB on AGC gain and 10 dB on LNA gain. That I kind of determined the signal was kind of stable and observable. But once again, I'd like to repeat a lot of steps. And by the way, compared to different software, I use two different software, and both one is the plain raw IQ, and another one it has a processing, but both of them are good.
Yeah.
Close
Beyond
to each
that,
other.
the 809361 chip in there, I think it has an AGC in the receiver, so you'd have to like t set the registers to lock that. I think if you want to be careful comparing amplitude.
Yes, what I'd like to do next also, because we have B200, which is USRP 2922 National Instrument, very good SDR receiver. Thanks to Bulat W6BBB who donated this to us. I spend now a lot of time, and that's a primary SDR receiver for us, which is going to be used for Artemis II. And I've been running Artemis II software on the background for days already, and it's super stable. I'm really satisfied. Nothing to compare to Pluto on anything. I can compare to B2210 clone Chinese or real one, but I can compare to the what is compared to what I have or other SDR receivers is excellent. So I'd like to use it. And compare to all of these data measurements to have multi layers because I don't want to. The last thing I want to do is to tell System One guys or our board that, hey, I determined 0.1 degree pointing error. I want to have proof this on numerous different waves so that we do have a pointing error, and this is critical for DSN or what else we can do. So I'm going to use all tools in my bucket to accomplish that. So next time we're going to come, I'm going to have a lot more tools, and anyone that want to participate to come, you're welcome. There's more brains we have on side. It's better because am I going to forget things? Am I going to do? And I really want to have someone on the back pointing out, but that would be very good. Any other questions?
Yeah, I have a question, Alex. This is Vlad. So did we ever try to characterize the loss in cables between dish and shack? And that also affected the measurements actually, and all losses across the feed and all that stuff.
Well, thanks for question, but we're not using RF cables, and RF cable losses not relevant to this because DSN system, as I mentioned, and I'm gonna go back to that. So I did not include the diagram, how everything is connected, but I want you to understand, unlike anything done before, we do not have RF losses. So before you had feed, you had preamplifier or DC block, whatever, and then you had feed lines going back to the shack where you had SDR
I got it.
receiver.
Yeah, you didn't need to explain.
Yeah.
Rest. Okay. Yeah. Fine. No problem.
Yeah. Well, I want to finish since my others can understand that. I want to stay away from any RF losses because that affecting your noise figure and all that if you don't have proper way of cascading your LNAs, which kind of we do have that now for Artemis, and I don't want to cover Artemis in this presentation, but the way I approach everything, the software processing, the RF, the integration, everything must be done in the feed. Nowadays, is everything achievable and doable on the hardware side? So DCPM module has a Raspberry 5 with it's actually a 2 terabyte hard drive in it, and has a second NUC 4-core processor separate there. Everything is directly connected to the SDR receiver. So you have a high-speed USB 3 connection, as you see on that, and that's the middle connector. That's actually USB connection 3 to the SDR receiver that mounted right at the front end. So you have an output from down converter that's connected directly to the SDR. There's no losses. 0.01 probably, one elbow SMA connector. So you have virtually no losses, which is insignificant for me. And then everything done processed at the software running there. So how we connect? We're just using fiber optic. You're remoting your computer. I remote the computer in there from the shack. Now imagine the situation that something goes wrong with the fiber. Do I care? No, I don't, because the software is still running there. The only that will affect that is a power loss or antenna is going to be not tracking or steering where it's supposed to be. So for Artemis II, for example, you can point antenna, let the system running completely independent. If you want to remote it and check it, see, but other than that, like for pulsars, you have to integrate over time, no matter what. You don't need to feed anything to the control room. Everything done there automatically, and then all is just download the data. Since we do have 2 terabyte hard drive, and I was running for 22 hours straight Artemis data collection in raw IQ format, it's only recorded 5 gigabyte of data, and that's 24 hours, nearly 24. So if you want to run for 10 days, that's not going to be enough to fool the solid state drive. And then when your software connected to the solid state drive for Raspberry Pi, they use a high speed. It's not USB. It's a high speed line. It's the enormous speed between them. So I like this approach.
But it's also for Voyager project, it's basically a converter. You convert from 8 gigahertz to, I believe, an SDR band lower.
452 megahertz, that's the alpha band.
Okay, and the converter characterization, did you measure it, everything?
Of course, it's already accounted in the formula.
Okay,
Yes.
okay.
Yeah. So it's similar to our site, Dwingelo in Netherlands, that they have a similar characteristics of the antenna. We always compare us to Dwingelo because we're close. They're 20 meters, we're 18, and they have slightly antenna gain more than us. They successfully detected Voyager and they posted on their blog. And also they did a bounce off the geostationary satellite using their dish. So it's for us, it's kind of a model. If they're successful in something, we certainly can achieve that. They were also successful in Eve project. We were not successful, and there are numerous issues associated with it, technical and then software support. But so we can always look and see if they can do, we certainly can, because the difference in the gain between 18 in meters and 20 meters not significant, especially in low frequency band. So anyway, any other questions? All right, thumbs up, right? Well, I pretty much covered everything on DSEN update, Paul, and I believe that was the second topic.
Yes, there we go. Took me a second to find the unmute button. That was great. I'm sorry. What was your question?
Well, I understand everyone was sleeping on the background while I was talking. That's why the cameras were off.
I wasn't sleeping.
I appreciate that. The question was, the second topic in your list was the DSN updates.
Okay. I'm wondering whether we had time tonight to do that.
No, that's why I want to say, is anything else besides that?
So Roger had a little thing he wanted just to I wanted him to kind of like highlight something about what's going to go on in the next 4 weeks or so. And Roger, are you still awake?
Yeah, I'm here, and let's see. Alex, can you stop sharing? Just so I get more real estate. There we go. I didn't realize you wanted me to present, Paul.
No. I don't want you to present. I just want you to kind of like just give a little bit of a spiel. Short. Just like what you were doing about volunteers and things. Just kind of high level.
Oh, okay. So looking at the Artemis, I mean, basically, it's in flight over 9 days, and approximately when the moon's up is when when we have. See, Alex just muted, so he can go to sleep.
I'm not muted. I'm here.
Well, not muted, but I mean, you went to a picture, just like you were joking. Yeah. So the trick is how do we staff? I mean, right now I see almost our biggest challenge right now is staffing the dish during the time that Artemis is up and we can gather data. And so I composed an email and sent it to the board to review. And now things have changed because we've now been accepted, and so I'm trying to.
Well, Roger, start with the earliest launch date. I mean, we're out of runway here.
Okay. Hold on here. Let me.
I don't know if everybody understands that, right? I mean, we're going to try to track Artemis, and the earliest launch date. That's the key. And then there's that week in February, and then there's the next two.
So launch windows are February 6th. Well, here we'll start with the first one, February 6th through 8th. And keep in mind, any launch during that time starts we'll call it a 10-day clock, where we have to be staffed while Artemis is above the horizon to collect this data. We'll put an asterisk after that. On Wednesday, I guess we'll find out if NASA wants us to collect data at specific times, or whether NASA wants us to collect data throughout the entire mission. Does anyone know, Rick, do we have any idea which one of those things is true, or we just don't know at this point? Whoop, you have to unmute.
Yeah,
A variety of questions have been submitted to NASA like that. And I will have hopefully answers to all the questions at the Wednesday morning team meeting with NASA. That's scheduled for 8 a.m. And as soon as I get answers, you will have them.
Okay. Are you the lone person invited to this, or can we
No,
listen in?
no, they only invite the point of contact from
Okay.
each of the
No, that's
35.
fine.
However, I might have someone here with me who's important and wants answers to questions. So I think Glenn may be here at my place during the meeting. And that's important for steering issues.
Okay. All right. So we don't know whether we have to have this thing staffed the entire 10 days while Artemis is above the horizon, or we just have to staff it during certain times. Now, given the fact that the launch date is approximately a week and a half from now, it's not, NASA isn't giving us a lot of lead time here. And so, should I send out an email asking to try to collect as many volunteers as possible at this point in time? Wait till Wednesday morning? That's kind of a question I've got.
I think you need to ask for volunteers now.
Now, okay. Well, then I will massage that email, and if the board is willing to give me permission, I'll take that original email and I'll tweak it a little bit and get it sent out like tomorrow. Board, is that okay?
Sooner
Yes.
better. Sooner better, Roger. Yeah.
Okay.
Tonight.
All right. So, and I've been, Bill, I actually forwarded an email that Lewis sent me. We have actually been discussing Perplexity's prediction, and he now kind of agrees with, he's crediting me with that, but it's you were the one that kind of came up with the fact, or approximately where in the sky Artemis was going to be. So, and if anyone's interested, and I don't want to get into discussing, how we're going to point or anything like that, but in that email, there's actually a really good picture. Let me see if I can share this. Share screen to share. Can everyone see that, or is something blocking the?
Yeah, that's pretty good. That's good.
Okay. So
Bigger might be better. I don't know. Can you do the top that's top down or top looking down? Yeah, just give us the top one. Can you do that? There you go. And then blow that up. There you go.
Whoops, I'm trying to,
Or slide it down. Yeah.
there we go. How's that?
That's good.
So, Bill and I had a discussion over breakfast, and I apologize. It turned into an email storm, but
I'm
he and
glad I
both
gave
kind
that to you.
of, yeah. Bill was like, "Yeah, I'm right behind you. 5 miles behind you." So, yeah, this is, so my guess, the way that Glenn is proposing to do this is for us just to periodically enter the current right ascension and declination. And I could see some problems going around the moon. I can see some problems early on, but a lot of that coast phase, the fact that this is over days, is that I think that an approximate right ascension and declination will probably work to keep us on well enough. Any idea how wide our beam width is in S-band?
You asking me?
It's about a half a degree, roughly.
Oh, okay. So it might be tight. I don't know.
0.8 with 1296, so it's a little bit tighter on 23 or 2.2.
Yeah.
We will have pointing information in apparent, from what I've been told so far, we will have the ability to choose from a variety of different formats by logging into the correct site and asking for the data in whatever format we want.
Oh, cool.
We're going to
Okay.
have to steer the dish.
Yeah, and the point here was that pointing vector to line of sight to the moon is a completely different thing than the pointing vector of the orbital track of the Artemis.
Yep.
And oh, by the way, that x-axis, it's not that can't be kilometers. That's got to be million kilometers or
It's
something.
times 10 to the fifth, way over on the far right. If you look
Yeah.
at
Okay. Yeah, times 10 to the fifth up there at the top, it says. That's right.
yeah. So okay, I'm going to stop sharing here. I'm going to I'll massage that email and get it out to DSES members. Actually, now that it's public, I might also post it in well, no, let's keep it to DSES members only. So I'll take that list and send it out. Is that what you're looking for
Yep.
Paul?
Yeah, that's great. And if you like, I can send it on a all members blurb on HCOL.
Now,
Yeah.
also, I want to, well, if we're coming on this up next weekend, right? So prepare yourself and any volunteers. If we can install the system, we have a perfect opportunity. One, verify the pointing of a dish and beam width for the S-band. Two, which is very important, actually point dish to the known object, one of the lunar orbiter, or anything that close to us and proximate Earth to detect the actual signal. That'll give us an idea, the antenna pointing and antenna performance, and we're going to be 100% ready. Before, we need volunteers no matter what, but we want to make sure that we're ready for that from our technical standpoint point of view. So I'd like to conduct all of this tests, and hopefully the weather will cooperate, and we're not going to
Supposed to
have
be
any other
perfect weather.
issues. So let's stay efficient. And I want to mention here because some of you are going to be there on site as well with myself. So we're determined to get as many tests as possible to prove as many points possible as well. So please, if you have time available on next weekend, Friday, Saturday, and portion Sunday, please come help us. As many hands on site we're going to have, as more training we'll conduct, because I'll be able only do remote sessions to verify the system performance. So I'm not going to be able to come to help with the antenna. So we have to look for volunteers.
Okay, I'll add a request that if people want to volunteer for the for monitoring Artemis, for that they come down Friday or Saturday. Sunday, by the time they get there, we're going to be tearing stuff down. So
Also mention the hotel needs. You have a special rate there too at the Cobblestone Inn.
okay.
Well,
Yeah.
Roger, we're not going to be tearing down anything. The system will remain to be there. We're not removing anything on.
Okay.
We'll keep the system fully operational. Perhaps we'll keep the system on, except just pointing antenna dish up and keep the system running in a fully remote session, because that's how we're going to be doing it.
Okay.
Like Rick does his hydrogen line scanning. We can stow antenna, keep the instrumentation on at the hub, as long as we have a certain percentage of confidence that there would be no rain or something going inside.
Well, that's the problem is because the lid now has that vent in it, there's an almost 100% chance that if it rains, water will get inside.
But we're only going to have 2 boxes there, so it's easy to waterproof, because I want to make sure we're not going to just postpone everything till the day when the launch day, and not knowing it's been working here for days, no problem. I'm 100% confident on my side, everything is functioning here, but I don't have weather factors involved. I don't have other factors involved at Haswell applicable only. So I want to make sure we there not going to find, and also I want to make sure Rick has his backup system running. So because he can use our system to also verify his remote session. So we gotta have 2 backup. Anyway, that would be ideal if we have the ability. If not, for whatever reason, well, we're just not gonna do it.
Okay, I'll see if I can think of a way to weatherproof that lid a little bit more.
I'll try to minimize the footprint of the system. So before we had numerous stuff. This time we will not, because first of all, the SDR receiver, it's over LAN. So we need to have just the LAN connection. There would no USB, nothing. So, and there would be no motor control. We don't need that. So it's going to be only power supply itself and the main module. So in the worst case, what we can do, we do have remote capabilities over internet to switch on and off. So we might going to add something so we can remotely switch on and off, because we do have that emergency stop. But in the end of the day, it's just a relay in a box. So if we can tie this relay to the control, AC control that Paul has, that's how he turns on and off PC in the control room, we can have capability to turn on and off the system. That would be great. If we need to turn it off, we'll turn it off.
Okay. I'll plan on it staying up there.
From the weekend till the day to February 6th, I believe it's 5 days, right?
Well, potentially April. Oh, I never finished. Do you want to hear all the other dates?
They're in the chat, by the way. Who posted them? Looks like Jeff posted all the dates in the chat.
Okay. And bear in mind, so we're told, it launches and then we are possibly on the hook for 10 days. Though I really don't think we're probably going to be able to make many measurements that first day when it's in that eccentric orbit around Earth.
Do we have an idea like how often the telemetry transmitter will be turned on? Like, is it going to be all on the whole mission, or do we know?
That's what we don't know. That's what Rick was saying is one of the questions I posted to him, and those questions have been passed to NASA and will hopefully be answered Wednesday morning.
Yeah,
I'm just taking a guess here, but I would think that one of the things that NASA would be the most interested in would be that point of TLI, since that's going to determine the whole trajectory. And I would think that their Doppler shift data is what they would be more interested in for that maneuver. And so I'm not sure when that occurs after launch, but I would think that would be one of their most important data points that they would like to see. Not just a guess on my part, but we might want to ask and see if that's true.
So TLI occur. These are all round numbers. Can everyone see you see that chart I put up again?
Yes. Okay,
so TLI occurs about a day after launch. And if you notice, TLI occurs at perigee. And this is an extremely eccentric orbit that is coming in lower than geosynchronous satellites. So it's booking. And I don't think that our telescope can keep up with that velocity.
Well, it depends which side the Earth's facing too, right?
Yes. Yeah. We have a 50-50 chance, right?
Maybe.
Yeah, and that's exactly the point where we're going to expect the maximum Doppler shift due to speed. So It shows that the TLI burn impulse, the radial velocity, going to be peaking about 3.2 kilometer per second away moving from Earth. So I expect to receive about 23.7 kilohertz Doppler shift as maximum throughout the 10-day mission.
Well, bear in mind, you're going to be measuring the Doppler shift, perpendicular to the way we're looking at it only.
Yeah, I'm looking at the trajectory comparison to the DSES side in that particular period of time, but we don't know what's going to happen exactly, right?
Yeah, see, my guess is from the course correction OTC1 to OTC3, it's going to be relatively easy to stay on. That's a gut level feel. I worry about OTC to RTC1 because things are speeding up there, but then you kind of you're almost looking along a pipe there from RTC1 to RTC3, and it should, a right ascension and declination should be able to keep it in the field for at least enough time to get some data.
So I was going to say, we'll find out probably Wednesday morning, and we can send out a note which gives all this information on our to all members, so that everyone knows when we're going to be doing this. I doubt that they're going to want us to do this when it's moving that quickly. It's probably going to be a longer thing, but we won't know until Wednesday morning. So rather than speculate, why don't we just wait a day?
Yeah.
Okay, Neil?
I guess that's it.
All right, you can stop sharing now.
Well, oh, here we go.
Yeah, that's better. Thanks a lot for all you've done there. This is great, Roger, and you and Alex have really stepped up and are what I consider super leaders in the Deep Space Exploration Society. So thank you very much for all your work. And I'll see you down there on the weekend. I'm picking up Alex Friday.
Yep, and I'm planning to be down there Friday through Sunday.
Perfect.
Paul?
Yes.
Two more things. So I will not able to contribute for February 6th weekend, but if lunch will be shifted to the later day, maybe. So, but definitely cannot do this at 6. Another thing, I just shoot you email. I donated PC.
I got it.
Yeah, you got it. Yeah, you will take care of pick it up. By the way, yeah, talk to Laughlin if you will see him in person. He's an excellent system engineer in space. In satellites, and he kind of interested to join DSES. Talk to him. He's a good kid.
Love to see him. All right, that's great. I'll give him a call tomorrow.
Okay.
Thank you. All right, everybody. Thanks again for all your attention, and your questions were great. And we're on to a really great adventure now. So all the best, and we'll talk with you guys later.
Yeah, and I will upload my presentation on the Group.io file section. So if anyone want to come and look at it, please do so.
Thank you. All right, 7-3, guys.
All right. Good night, Paul.
Good night.
Good night.